Log on, tune in, find out. Another good idea from Cambridge.
Good morning is Arun Ram, who will continue this series of talks.
Okay, great, thanks. Yeah, so if the title of this was Symmetry, Polynomials, and Quantization. So if the first two were symmetry, about symmetry, this one is sort of about quantization. But I don't really know what quantization is, so I'm going to make it up, my own version of quantization. So I want to start with, well, let's just start with my two dual lattices. So these are dual Z vector spaces, which are paired with a pairing which I denote with these angle brackets. And what I want to, I think I go here now. So the group algebras, I can write that here. The group algebras of these lattices, so these are abelian groups. And the group algebras I want to call kt of a point. So this is the span of x to the mu, where mu is in hz star, with x to the mu, x to the nu equal to x to the mu plus nu. So I write the group hz star multiplicatively, and this is the group algebra. And kt check of a point is the other one. So it's exactly the same, but with the other lattice. But it's very important that I want you to think of these as polynomial rings. So in n variables, or Laurent polynomial rings in n variables, one is in x's and one is in y's. And of course the conversion here is that x to the mu is x1 to the mu1 up to xn to the mu n. So what I'm going to do is, as usual, the only way that I can work with a vector space is to choose a basis. So epsilon 1 up to epsilon n is a basis of h z star, and epsilon 1 check up to epsilon n check is a basis of hz of hz. So I have a similar thing for the y's. So somehow now I wrote kt of a point. So that means the T equivariant K theory of a point in my head. And it is exactly this polynomial ring, if T is a nice torus. Okay, so I somewhere in my head, quantization has to do with a passage from cohomology to K theory. So I will not make that precise in this lecture, but I want it to be in the background so that if you know about equivariant K theory, then you are thinking of it. Okay, so now I want to let q to the 1 over e be a parameter. So the Heisenberg group then, is the group q to the k over e, x to the mu, x to the mu, y to the lambda check, where k is an integer, mu is in the first lattice, the star lattice, lambda check is in the hz, with, so what are the relations that I need? Well, I need those relations. So what should we call these? Let's call these relations star. I don't want to write them again. So with star and so this relation, I don't know, I couldn't think of a good name for this group because I'm going to need H for other things. So I don't want to call it H, but what should we call it? Heisenberg group. What? Anybody have a favorite name? Let's call it Q for now. So this statement, parameter, is a fancy way of saying that I want this thing to be in the center of Q. It commutes with everything else. So when I use the word parameter, it somehow means something that commutes with everything else. And finally, the last relation, which is the one which makes it an interesting object, is that to push the x's past the y's, you get this central extension popping up. All right, so that's that Q. All right, so now we start over again with two dual vector spaces. And a form pairing them. So one of the themes, which I'm sure it will be more of a theme next week, is if you remember, I had a reflection group. And there's a world of Z reflection groups. Those are Weyl groups. And then there's a world of complex reflection groups. And one of our dreams is to make the theory of Z reflection groups all work without case-free for complex reflection groups. So this fight is starting to appear. How to make things work for the complex setting. So now here we have the symmetric. So there's a parallel story somehow. So the symmetric algebras are ht of a point, which I will call this way, and ht check of a point, which I will call this way. And with, of course, I'll use the notation that x mu is mu1, x1. Actually, I want to call these d's. Sorry, d1 up to d. Mu1, x1 up to mu n xn if mu is mu1, epsilon 1, mu n epsilon. And then similarly for y's, or d's, there will be d lambda checks, which are lambda 1, d1 up to lambda n dn if lambda check is okay. So I have a cohomology story, and on the cohomology side, we're going to let kappa be a parameter. And the Weyl algebra, so this, sorry? Sums. So this is just a notation for the linear vector mu. These are symmetric algebras. Maybe that's, I should say it this way. This is HC star, and this one is SHC. That may help. Okay. And so the Weyl algebra so let's call it curly D. This is the thing which appeared in Pramod's talk yesterday, is generated by these two polynomial rings, Cx1 up to xn, and Cd1 up to dn, with a relation which says that d lambda check x mu is equal to x mu d lambda check plus kappa times the inner product. Okay, so that's the usual one where, as Pramod explained yesterday, you've seen this. This dx on polynomials. So if we take our two bases to be dual, for example, and maybe we take kappa to be 1, then di would act by the partial derivative with respect to xi, and this relation is the same as the well, sometime in your life you have to convince yourself that as operators, the commutator of xi and del by del xj is delta ij, and you should actually remember that this is not delta ij, but this is this form. So this is the usual. This is where the differential equations come from, and of course, maybe I remark that sometimes in physics, kappa is I h bar, and x is called p, and d is called q, and one is called momentum, and one is called position. So we actually are not so far from what's going on in quantization in a physical sense. Okay, great. So that's the motivation for the rest of the story here. So now we want to introduce our reflection group. So let's so W naught is a finite subgroup of GLHC. Okay, generated by the reflections it contains. So R plus is the set of elements that are reflections. A reflection is an element whose fixed space is codimension 1. So, okay, so now the group algebra. So I'm going to need the group algebra of this. The group algebra is the span of some symbols T sub w with, of course, TW1, TW2 equal to TW1, W2. So I'm just taking the group and making it into an algebra. You see that this Weyl algebra is an algebra, so I need to be in the world of algebras. Okay, now I need some data, which I alluded to on the first day, but let's do it again so that it's fresh. So first thing is, let's recall that W naught acts on the dual space by the dual representation. Okay, so and what I want to do now is for each reflection, I want to choose a root and a co-root. So let's fix alpha sub s in HC star and alpha sub s check in HC, so that, and the real reason I want to do this is so that I can write a formula, a nice formula for the reflection. So the reflection S acting on mu is mu minus mu alpha s check alpha s. And it's convenient, especially since I have these two dual vector spaces, to make it symmetric in some between the two in some sense. So all right, so this I want these nice formulas for the reflection. So that's why I choose roots and co-roots. And of course it's also convenient that if I can get from one reflection to another by conjugating, then I would like the corresponding root to be the image under W. So this is natural to ask for. And similarly for the co-roots, actually one implies the other, but that's okay for W in W now. Yes, thank you. Thank you. Otherwise, it's not symmetric, right? Okay, good. All right, now, if you think about so the fixed point space of the fixed space of S is codimension 1. So that means there's a one-dimensional space which alpha S must span. But alpha S is not uniquely determined in that it's a line. So I could multiply it by a constant. Once I choose alpha S, then alpha S check will be determined. But there's still a constant degree of freedom. So I'm going to keep track of that. So introduce parameters which are called C sub s. So in the literature, we usually put one for each reflection. That's convenient, but that's not really the truth. What the truth is that I want only one for each orbit. Okay, I mean, it should make sense. I want the vector alpha s for a conjugate reflection to be the same length. And so I should require, so these are the lengths of these roots, and I view them as parameters. Okay, so I think I have now all the data that I can, let's see if I can, I think I can get those formulas on one board. So the rational Cherednik algebra So this is called blackboard bold H tilde. So this is generated by polynomials in the x's, polynomials in the d's, and the group algebra of W naught. So it's polynomials in the x's, polynomials in the d's, and that symmetry with the following relations. So T sub W x mu is x W mu T sub W. T sub W d lambda check is d sub W lambda check TW. So those should feel very natural. I want it to be some kind of semi-direct product. And then the interesting relation is the following one. It says that d sub lambda check x mu, so you should be reading this, is x mu d sub lambda check plus kappa, the inner product of mu with lambda check, minus the sum over S in R plus CS lambda check alpha S mu alpha S check T sub S. Okay. This is the rational Cherednik algebra. It's exactly like the Weyl algebra, but there's some extra garbage. But all that garbage is in the Weyl group. It's an amazing object. So it really looks like it satisfies a PBW theorem. So that means that it really has a vector space. This algebra is really one polynomial ring, the group algebra of the Weyl group, and the other polynomial ring. Okay, so so that's the PBW for the rational Cherednik. Okay, so now the most important representation of the Weyl algebra, obviously, is the action on polynomials. And so one would expect that the most important representation of this object should be an action on polynomials. So that's what we want to set up now. So first let's note that if P is a polynomial in the x's, then you can compute how to push d lambda check past P. So I'm going to, this is for a linear function. Now I'm going to take some higher degree polynomial and push it past. And you get P d lambda check plus kappa times d lambda check P. I will define this in a second. Minus the sum over the reflections, CS lambda check alpha sub S. And del S P TS. So this mu lambda check generalizes to this d lambda check P, and this mu alpha S check generalizes to this delta SP. So let me tell you what those are. So d lambda check is this map from polynomials to polynomials given by, so d lambda check on a linear function is the inner product. Well, that better be, because I want that formula, this to be the linear version of that formula. And d lambda check on a product is P1 d lambda check P2 plus d lambda check P1 P2. So in other words, this little d lambda check is a derivation. That's what this is. It's the unique derivation with this form. And this del S, so let me write this polynomial ring this way again. So if we think about what it would have to be, or you compute it, or whatever your favorite way is this operator. So del S acting on P means take P, apply the reflection to P, subtract them, and divide by x alpha S. This is called the BGG operator. So BGG operators appear very naturally as push-pull operators or correspondence operators in the cohomology of the flag variety. So if I were looking at cohomology of a flag variety, I would get these operators appearing. Here, they're somehow appearing of their own accord from this relation. So, okay. Do I have to divide by?
Alpha is check. We put this in
No, I don't need to. that question is related to some desire for some integrality. And here I'm working over the complex numbers, so I don't know what my integers are. Okay, so now the subalgebra of the rational Cherednik algebra, so I'll call it H without a tilde, generated by polynomials in the D's and the group algebra. So this is a subalgebra. This is half. This is this right-hand half. Halves always include some middle part, some carton. Okay, so this subalgebra has a one-dimensional module, which I will call span of one basis vector 1, given by, so T sub w, that's this vowel group part, acts on 1 by the trivial representation, and d sub lambda check acts on 1. Well, think about my Weyl algebra. In the ordinary Weyl algebra, this is a derivative. And derivative of 1 should be 0. So that's my one-dimensional representation of this subalgebra. And the polynomial representation of the rational Cherednik algebra representation of the whole thing now is the induced representation. So I just induce this one-dimensional representation from H to H tilde. So I like to think of that as just taking 1 and acting by H tilde. So if you feel like you have to put a tensor there, that's okay with me. But it's clear that when I take elements of H tilde look like this. So by this BBW theorem, all this stuff gets killed by 1. So all that's left is C x1 up to xn 1. And so this looks like polynomials. Okay, so now we can write down, I think I can put it. So d lambda check acts on this polynomial representation by the Dunkel operator. So this is the definition of the Dunkel operator. So it's the action. So unfortunately, I'm going to call it d lambda check again. But now I'm talking about the action of d lambda check on the polynomial representation. And we can write it down just by looking at that formula on the top of the board there. We can write down how it acts on polynomials. It acts by kappa little d lambda check minus the sum over s in R plus cs lambda check alpha s 1 over x sub alpha s 1 minus s. All right? So as an operator on polynomials, this is what d lambda check is. Now actually, that polynomial representation is a faithful representation. So I often play a game of ignoring the difference between the operators and the elements of the algebra. That's common to do that. If you read Cherednik, you must do that because otherwise you're completely confused. So sometimes I just identify d lambda check with this operator, or I identify the rational Cherednik algebra with its image in operators on polynomials. Okay, so that's the Dunkel operator. Great. I seem to be, I think I'm going fast today or something. I seem to be ahead of where I expected to be. Are there any questions or something? Yeah?
is R plus.
R plus, yes, it's R plus. Okay, let's continue. Well, I want to continue with now going back to this reflection group, and let's look now at the case when W naught is a finite subgroup of GLHZ. Okay, so let's go back to the vowel group case. That works for any complex reflection group, W naught. All right, generated by R plus. Now, in this case, W naught has another presentation of W naught, has generators S1 up to Sn, and relations Si squared is 1, and Si Sj Si is Sj Si Sj, where there are Mij factors on each side. So as before, where this pi ij, this Mij is given by the angle between the reflecting hyperplanes. And now this makes sense, the angle between the reflecting hyperplanes, because everything is sitting inside of a real vector space, and in real vector spaces I know what angles are. So this Coxeter representation is available. This is the Coxeter representation of W naught. Okay, let's see. There's something else I need before I. Oh, right. So just to make life interesting, let's create another copy of the symmetric algebra on H. So y lambda check is lambda 1 y1 plus up to lambda n yn. If lambda check is lambda 1 epsilon y check. So I would like to use the d's that I was using before. These y's are serving somehow the same purpose as the d's in this case, but I can't quite use the d's. They're not equal, so I have to create a new copy of this thing. All right. So I wonder if I should keep this. Let me keep that board for reference. And let's, for analogy, let's work over here for a moment. Okay, so the trigonometric Cherednik algebra will be called HGR tilde. So this is generated by so I have my polynomials in the y's. I have my group algebra of the lattice. Notice I cannot do this. I cannot build this trigonometric Cherednik algebra for an arbitrary complex reflection group, because I do not know what this lattice is. Okay, so this is one of the struggles. We would like to know how to build a trigonometric Hecke algebra for non-Weil groups. Okay, so this is generated by these things with, so T sub W x mu is x to the W mu T sub W. T sub Si y sub lambda check is y sub Si lambda check T sub Si plus C sub Si lambda check alpha I for I going from 1 to n. So this is exactly the relation which Sasha Kleshchev used in his degenerate affine Hecke algebra. All right, so that's appearing here. And finally, there's a relation for taking the y's. The y's are analogous to the d's up there, past the x to the mu's, which is x to the mu y sub lambda check plus kappa mu lambda check x to the mu minus the sum over s in r plus cs lambda check alpha sub s x to the mu minus x to the s mu over 1 minus x to the alpha times t sub x. So this relation, this relation is what my Weil algebra relation has become. All right, so this is the same relation somehow one step before. And for me, we're now looking at a quantization. This one is somehow a quantized version of that one. We would like to make that more precise. All right, so, okay. So I better put that up, the rational Cherednik algebra. Okay. Sasha, where are you? No, that's only a point. Thank you. Great. Okay, unfortunately, I have gotten a Mobius band going here. So the sequence of this board is that one, and the sequence of this board is this one. Okay, because everything is analogous. Now I'm going to create a subalgebra. So this will be called HGR, generated by polynomials in the y's and the group algebra. So this should be analogous. Has a one-dimensional module, which is again I will call span of a single basis vector, which is called 1, given by so we want it to be the trivial representation on W naught again. We want this to be. But then you can just compute that this thing does not allow you to let the y's act by 0. So that relation, this cannot be 0. Otherwise, that relation is not satisfied. However, you can use that relation to compute what it has to be, and the answer is rho sub c lambda check, where rho sub c alpha I check is c sub si. So this is some analog of rho in Lie theory of the half sum of the positive roots. And it just appears naturally from that relation and this relation. Okay, so now we can make the polynomial representation of the trigonometric Cherednik algebra. Representation of the trigonometric Cherednik algebra the same way. So it's induced from HGR to HGR tilde of the trivial representation. So that's HGR tilde 1. And again, there's a PBW theorem in place which allows me to write this as the T equivariant K theory of a point. Okay. So this one is cohomology, and this one is K theory. All right, if you believe my funny notation. Okay, so we can ask. So the game is to ask, well, how does y lambda act on this polynomial representation? So before that, let me just make a remark that the operator, which we might call pi s, which is appearing already in the relations. So pi s acting on x to the mu is x to the mu minus x to the s mu over 1 minus x to the alpha. So we see that. That pi s, I wrote it out, but that pi s was appearing here. And in the Cherednik case, it's erased. In the rational case, if you remember, that thing which appeared there was a BGG operator. And this thing is called, is a de Mazur operator. And if you go back and think about or go back and read where did it come from, it came from the equivariant K theory of a flat variety. So all of this analogy between K theory and cohomology is too, it just feels too strong to be a miracle, to be a magic. There has to be something going on. Okay, so let's try to write down how that acts. And let me put it here. So y sub lambda check acts on the polynomial representation of the trigonometric algebra by what's called the Dunkel-Cherednik operator. And the Dunkel-Cherednik operator is y sub lambda check is equal to rho sub c lambda check plus kappa times a new d lambda check minus the sum over the reflections of cs lambda check alpha sub s 1 over 1 minus x to the alpha 1 minus x. So it should look very similar, but not quite the same. And here, if you allow me to continue my sentence over here, where this del lambda check is a map now from Laurent polynomials to Laurent polynomials. which is given by del lambda check applied to x to the mu is mu lambda check x to the mu. So it's exactly what it has to be. The relation, it's right there. I've just written it in a different form. This term that's appearing here is the same as the term that's appearing here, and I've written it in a different form only to make these operators look similar. Okay? All right. So now the question is, can we make these the same? And so let's go back one step, and let's ask ourselves, do we think that these two polynomial representations are the same? Well, of course they are. We know that they are. There's something called the Chern character, and the Chern character takes a homogeneous line bundle here to e to its first Chern class. So in some, you're bothered about the direction? Yeah. Yes, that's right. You should be. But I want you to think of it this way. I mean, after some completions and after extending a little bit, it's an isomorphism. All right? So usually you worry about this. You have to tensor. It only works over Q, and then you have to complete. So that's one version, say, of a T-Siegel completion theorem. Okay. So we would hope that we can do something similar and actually make this rational Cherednik algebra isomorphic to the trigonometric Cherednik algebra. But of course, we don't expect to make it exactly isomorphic, because even here there's a completion. That's why it's called a T-Siegel completion theorem. Right? So this isn't quite an isomorphism, but it's very close. All right, so what do we do? So the answer is actually, once you have this going through your head, you just have to get the unwind the formulas. So let's let x to the mu be e to the hx mu. So now I'm thinking of this right-hand side. I'm thinking of this as an element of, say, this thing. So I've introduced some parameter which I call h, and I'm thinking of power series in h with coefficients in the rational Cherednik algebra. So if you're used to quantum groups or something, if you think about quantum groups like Drenfeld, this is a very common thing to do. Let's take power. This is how you build deformations of algebras. All right? So it's not so weird to try to write this down. Okay. So then what do you get? Well, then, of course, you observe that this operator, del lambda check, is actually equal to 1 over h times this operator. Okay? This is the operator. And what does it do? It just pulls down that constant corresponding to the derivation. Well, this is the derivation, which pulls down that constant. And I have to divide by h because the derivative of e to the h is, the derivative of e to the hx is h times e to the hx. So, all right, so these two things are equal. So now you notice, so that means I have a relationship between this little d lambda and this partial lambda check. But I can write capital D lambda in terms of little d lambda, and I can write y lambda check in terms of partial d lambda. Right? And that's the isomorphism. So So now let's write down a map, a sort of map, a somewhat map. Let's take H tilde GR here, and well, let's write it, make it analogous here. So this is H tilde. Maybe I need to add some forming power series there. And I want, in this map, I want x to the mu to go to e to the h x of mu. And I want partial lambda check to go to 1 over h d lambda check. So already, this is the problem with this, is we try to make it an isomorphism. Already we have problems because we have to divide by h. And in that thing, you're not usually allowed to divide by h. So usually, we put a reg here, which is supposed to let you divide by h. OK, then you put t sub w equal to t sub w. And actually, now we're done, because we can use these two formulas to solve for y sub lambda check. And let's see if we can just do it in our heads. So y sub lambda check is rho c lambda check plus kappa times. So here I need to put a 1 over h d lambda. So let's just put 1 over h capital D lambda check. And now I have to put some correction factor, which should be the sum over s in r plus of cs lambda check alpha s times 1 over x sub alpha s, x sub alpha, times 1 minus, let's put an h there, okay, so I don't know what I need to do here. Let's just leave it. Okay, so this x super alpha has turned into e to the h x sub alpha. All right. And, oh, I don't need that. So that's that term. This 1 over x to the alpha s is this term. Oh, I do need it, because I took it out. I'm trying to do too many steps at once. Let me write it the easy way. Okay? So this is this term. This is this term. They're both going to come up. I just solved for y lambda in terms of d lambda. And there's a formula. Now, the reason I wanted to pull this 1 over x to the alpha out is I like to make this rational function so that I can expand it. All right? And you usually do that. This denominator begins with hx to the alpha, so I like to put something to cancel hx to the alpha and then fix it up so it looks like a better power series. But we don't have to make it look like a better power series. This is the isomorphism. Of course, it's not an isomorphism unless I'm careful about dividing by x alpha and dividing by h and so on. So all the subtlety of the difference between trigonometric toroidal algebra and rational toroidal algebra is contained in this formula. If this formula, if you're looking at a representation on which this formula is valid, then those two algebras look exactly the same. If you're looking at a representation on which this formula is not valid, say if x alpha acts by 0, then you're in trouble. All right, so, but otherwise, they're more or less isomorphic. Oh. Alpha is the same as alpha s. Yeah. My student told me he didn't like too many subscripts, so we should take them off. But Alpha is the same as okay, that's all I have to say. So if there are questions.
Are there questions, remarks?
Subscript GR. Does it have anything to do with grading? Graded? Why is it GR?
Yes, yes. So yes, it's true. So if so the reason I call this GR is because there's another object here, which is the double affine-Hecke algebra. Double affine-Hecke algebra. Okay. Which we talked about on the first day. And actually, that's, again, a quantization. So this is Chern character in the x's, and this is Chern character in the y's. So in this algebra, the y's are still a polynomial ring, still a cohomology. Right? Here, the x's were in cohomology, the capital X's were in K-theory. But the y's are still in cohomology. They're still in ordinary polynomial. So I would like to quantize those. And the formula here is, so if you remember this double affine-Hecke algebra had a y to the lambda check, and this goes to e to the, now I need another parameter. And x to mu, x to mu. So there's yet another quantization, and in this sense, that's that algebra is the cohomology of this algebra. In other words, this is the associated graded of that case.
Further questions?
Maybe that's a question for the afternoon question session, but I see polynomial rings and you use the words cohomology and K-theory, and maybe you can elaborate a little bit. I mean, I see.
Yeah, probably. Okay, that's good. It's good that you prepped me on that so that I can think about it. But probably I can elaborate on that.
Okay, then let's thank Arun again.